and the Deep Impact spacecraft is on its way to catch up to Tempel 1 in July.
4, 3, 2, 1.
Oh, wow. Awaiting visual confirmation.
NASA's Deep Impact probe just did something shocking. It crashed into a comet called Tempel 1 on purpose. This crash let scientists see what was hiding inside the comet for the very first time. What they found was jaw-dropping. Ice, dust, and even the building blocks of life, all floating in space. This discovery made everyone wonder if comets might have helped start life on Earth. But the truth is that they discovered something even more terrifying. Join us as we reveal what the NASA probe discovered in the darkest part of the galaxy, Tempel 1's terrifying discovery. In 2005, NASA did something really cool with a mission called Deep Impact. Instead of just flying by a comet to take pictures like before, they decided to get up close and personal with a comet named Tempel 1. They did this by sending a special part of their spacecraft to crash into the comet on purpose. This wasn't just for a spectacular space fireworks show. They had a big goal in mind. They wanted to see what was inside the comet by making a bit of it explode out into space where they could study it. This was a first-of-its-kind mission to actually dig into a comet and see what's beneath its surface. The crash into Tempel 1 was a big deal. It kicked up a huge cloud of dust and stuff that was inside the comet, showing us that the comet was kind of like a giant space snowball, but even softer, more like a fluffy pile of powder snow than solid ice. Imagine throwing a snowball that's so light and fluffy, it feels like it's barely there. That's what the comet was like. But here's where it gets even more interesting. In that big cloud of dust and ice, scientists found lots of organic materials and water ice. Organic doesn't just mean natural here. It means the kind of chemicals that can make up living things. Finding water in these organic materials was a huge hint that comets like Tempel 1 might have played a role in bringing the stuff needed for life to Earth a long, long time ago. The inside of the comet, where all this stuff was before the impact knocked it loose, was super well protected from the sun's heat. This means that everything inside it was like a time capsule from the very beginning of our solar system. It hadn't changed in billions of years. This was a game changer for scientists because it gave them a peek into what the early solar system was like and how planets and life as we know it might have started. The discoveries made by missions like Stardust and Rosetta have significantly advanced our understanding of comets, challenging and refining our theories about their origins and composition. Comets are intriguing remnants from the solar system's formation, composed of dust, rock, and ices, including frozen gases like carbon dioxide. These cosmic snowballs, when brought closer to the sun, heat up and release gases and dust, creating a glowing head and a tail that can stretch for millions of miles. One of the key revelations from these missions was the complex makeup of comets, including the presence of a wide range of organic compounds. The Stardust mission, for example, was the first to return samples from a comet to Earth, providing direct evidence that comets contain ancient building blocks of the solar system. The analysis of these samples revealed unexpected materials, suggesting that comets have a more diverse origin and history than previously thought. Stardust's discovery of glycine, a fundamental building block of life, in the samples from Comet Wild 2, hints at the potential role comets may have played in delivering the ingredients necessary for life to Earth. The Rosetta mission, which closely orbited Comet 67P, Churyumov-Gerasimenko, and deployed a lander to its surface, opened new avenues for understanding how comets are formed and how they evolve over time. This mission provided unprecedented insights into the composition and structure of cometary nuclei, shedding light on the interplay between ices and non-volatile materials in comets. The data collected by Rosetta are crucial for understanding the origins of water and complex organic compounds on Earth, offering clues to the early conditions of the solar system. Comets, often referred to as frozen leftovers from the formation of the solar system, serve as a valuable window into the past, offering clues about the conditions that prevailed when the planets were forming. Their study not only helps us understand the history of our own planetary neighborhood, but also informs the search for habitable environments beyond our solar system. The ongoing and future exploration of comets, facilitated by missions like Rosetta and technological advancements in sample return capabilities, continues to push the boundaries of our knowledge about these ancient celestial objects. Adding a personal touch to space science, the Deep Impact mission carried a CD with 625,000 people's names all the way to Comet Tempel 1. This Send Your Name to a Comet campaign was a way to get folks like you and me excited about space and feel like we were part of the journey. Even though the spacecraft had a bit of a hiccup and went into safe mode after it started orbiting the sun, it still did an amazing job. It sent back lots of data that told us Tempel 1 probably came from a far-off place called the Oort cloud and was mostly empty space inside, like a cosmic sponge. Scientists have been keeping a close eye on Apophis, an asteroid that's shaped kind of like a peanut. This shape isn't unusual for space rocks near Earth, especially those about the same size as Apophis. In 2029, this asteroid will come really close to Earth, giving scientists a great opportunity to learn more about it. They're interested in how fast it spins and whether the pull from Earth's gravity will change that spin. This close visit might even shake the asteroid up, causing asteroid quakes that could change the way it spins through space. After Apophis swings by Earth in 2029, a spaceship called OSIRIS-REx, which will then go by the name OSIRIS-APEX, will get a closer look at it. The mission is all about studying the asteroid's outer layer and what it's made of. Even though this spaceship won't be taking pieces of Apophis back to Earth, like it did with another asteroid named Bennu, the hope is to learn a lot by just observing. Scientists are particularly eager to see if being near Earth changes Apophis noticeably. We've just seen a comet up close. Now let's find out what happened when we crashed into it. A massive explosion. The Deep Impact mission was a big deal because it involved two pieces: a spacecraft that flew close to the comet Tempel 1 and a smaller part called the impactor. This impactor was pretty heavy, weighing 820 pounds, and was mostly made of copper. They chose copper because it wouldn't mess up the experiments they wanted to do. The plan was to have this impactor crash into the comet on purpose. It hit the comet really fast, at a speed of about 6.3 miles per second, which is super quick. This crash made a big boom, kind of like setting off almost 5 tons of TNT explosives. What happened next was like watching a space fireworks show. The collision made a huge cloud of dust and stuff fly off the comet, showing us that the comet was made of not just rock and ice, but also some really fine dust and even some complex organic materials, which are the kinds of things you find in living organisms. The impact revealed a wealth of information about Comet Tempel 1. It was discovered that the comet has a very fluffy structure, primarily composed of fine dust that is weaker than a bank of powdered snow, but held together by gravity. The surface of the comet displayed what appeared to be impact craters, and the analysis of the comet's ejection plume after the impact showed a significant presence of carbon-containing materials and water ice. This suggests that comets contain a substantial amount of organic material, supporting theories that comets may have played a role in delivering the essential building blocks of life to Earth early in its history. Furthermore, Deep Impact's observations indicated that the comet's interior was well shielded from solar heating, suggesting that the ice and other materials deep within the nucleus are likely in their original state from the time of the solar system's formation. The mission also identified various compounds thought to be part of the recipe for planets, comets, and other solar system bodies, including silicates, sand, clay, carbonates, iron-bearing compounds, and even aromatic hydrocarbons. One of the most amazing missions was the epoxy mission, which included the Deep Impact Extended Investigation, which involved a flyby of Comet Hartley 2, and the Extrasolar Planet Observation and Characterization phase, which used the spacecraft to observe nearby stars with known large planets. This extended mission provided additional insights into the diversity of chemical makeup among comets. It contributed to our understanding of the conditions under which comets, and potentially other solar system bodies, form. One of the most significant findings from the mission was the discovery of water ice on the comet's surface, confirming for the first time that comets could carry water ice in their compositions. This discovery is crucial because it lends weight to theories suggesting comets might have played a role in delivering water and possibly organic materials to Earth, which could have been essential for the development of life. The presence of water ice, however, was found to be surprisingly scarce, covering less than 1% of Tempel 1's surface. This suggested that the comet's gas and dust cloud might be primarily fed by underlying ices, challenging previous assumptions about cometary behavior. Moreover, the mission revealed that Comet Tempel 1 has a very porous structure, filled with a fine, powdery material weaker than powdered snow, but held together by its own gravity. The discovery of a significant amount of carbon-containing materials in the comet's ejection plume hinted at the substantial presence of organic compounds, further fueling speculation about comets' roles in the genesis of life on Earth. Deep Impact sent back about 4,500 images, providing invaluable data that helped refine our understanding of comets' origins and compositions. The images and data suggested that Tempel 1, and possibly other comets, originated from the distant Oort cloud, a vast reservoir of cometary bodies far beyond Pluto, and that the comet's structure is more empty space than solid matter. In addition to these discoveries, the mission's approach to studying comets was a significant departure from previous missions. Unlike earlier flyby missions, Deep Impact was designed to actively interact with the comet by ejecting material from its surface. This aggressive approach allowed for a more in-depth study of the comet's composition and structure, providing insights that were not possible with passive observation methods. After its main mission, the spacecraft embarked on an extended journey called Epoxy, which combined two major objectives: the Deep Impact extended investigation to study comets further, and the extrasolar planet observation and characterization to observe planets outside our solar system. The mission utilized the existing Deep Impact spacecraft, repurposing it for these new goals. On November 4, 2010, Epoxy made a significant flyby of Comet Hartley 2, marking a rare close encounter with such a celestial body, and providing valuable insights into its characteristics. The Epoxy mission revealed fascinating details about Comet Hartley 2, such as its active emission of fluffy ice particles from its rocky ends, and the discovery of water and carbon dioxide-powered jets that varied across different regions of the comet. This close-up study of Hartley 2's composition and behavior added to our understanding of cometary processes and the diversity of cometary bodies in our solar system. Moreover, the mission's observations of extrasolar planets aimed to deepen our knowledge of the physical properties of these distant worlds, including the potential habitability of planets beyond our own solar system. The Epoxy mission, repurposing the Deep Impact spacecraft, embarked on an innovative exploration of extrasolar planets through its Extrasolar Planet Observation and Characterization segment. This part of the mission utilized the high-resolution instrument for photometric observations, which are measurements of light intensity of known transiting extrasolar planets. These observations, conducted from January to August 2008, were pivotal because they allowed the spacecraft to monitor the light emitted by stars and any changes in this light caused by planets passing in front of them, known as transits. The mission managed to capture a staggering 198,134 images during this period, providing invaluable data on the physical properties of giant planets and searching for smaller bodies down to about half the diameter of Earth. One intriguing aspect of Epoxy was its observation of Earth as if it were an extrasolar planet. This provided a unique perspective on how Earth might appear to distant observers, offering a benchmark for characterizing Earth-like planets in future missions. The mission observed planetary systems where the known transiting planets were generally as large or larger than Neptune and orbited very close to their parent stars, resulting in short orbital periods that are easier to detect from space. Epoxy's observations targeted stars with known planets to ensure that at least one planet could produce observable transits. It aimed to detect small details in the brightness of the star during a transit that could indicate the presence of rings or moons around the planet. Additionally, Epoxy searched for variations in the orbital periods of known planets, which could suggest the gravitational influence of other unseen planets in the same system. The target stars for epoxy included HAT P4, XO3, Tri-S3, XO2, and GJ436, among others. Each of these stars was chosen because they host planets that transit their stars, making them ideal candidates for detailed observation. By comparing these observations with our understanding of Earth, the mission hoped to glean insights into the characteristics that might indicate habitability on distant worlds. The aerogel collector on Stardust was like a cosmic dustbin that could catch tiny pieces of space dust without messing them up. This was really important because scientists wanted to study these bits of comet and stars just as they were in space, without any changes. Aerogel is almost like magic. Although it's solid, it's so full of air that it's hardly there at all. When Stardust flew through the cloud of particles coming off Comet Wild 2, this aerogel gently stopped those speeding particles, capturing them like flies in a spider's web, but without squishing them. This was a clever way to get a close-up look at the stuff comets are made of. And it turns out they're a lot more interesting and complicated than just balls of ice and dust. One of the coolest things Stardust found was something called glycine, a simple amino acid that's part of the recipe for life as we know it. Finding glycine on a comet was a huge deal because it supports the idea that comets crashing into early Earth could have brought the very ingredients needed for life to start. This was the first time scientists had ever found an amino acid in space like this, and it made everyone wonder if life on Earth might have had a little help getting started from the stars. But Stardust wasn't done yet. After its main job was over, it got a new mission called Stardust Next. This mission was like a sequel in a movie series, where the hero returns to a place they visited before to see what's changed. Stardust went back to check on Comet Tempel 1, which had already been visited by another spacecraft called Deep Impact. By comparing how the comet looked now to how it looked before, scientists could learn how comets change over time. When Stardust flew by Tempel 1 in 2011, it took lots of pictures and gathered data that gave scientists new insights into how the comet's surface had evolved since the last visit. In 1978, astronomers discovered a comet named Wild 2, which had a path around the sun that made it an interesting target for a space mission. The comet's journey brought it close enough for a spacecraft named Stardust to visit. In January 2004, Stardust made a daring close approach to Wild 2, getting within 149 miles of the comet, which is really close by space standards. This brave little spacecraft had a mission to catch particles of dust coming off the comet, and it did just that, scooping up thousands of tiny pieces of comet dust and bringing them back to Earth. The return of this comet dust was a historic event. On January 15, 2006, the container holding these precious samples parachuted down to Utah. This was a big moment because it was the first time NASA had managed to bring back samples from space that weren't moon rocks since the Apollo astronauts did it more than 40 years earlier. After exploring comets, there's more space stuff to find. Next up, catching comet dust with Stardust and alien molecules. What Stardust found in those samples was mind-blowing. Among the dust, scientists found complex organic molecules. Organic molecules are the building blocks of life, so finding the intriguing idea that comets could have played a pivotal role in seeding life on Earth has garnered support from various scientific studies. These celestial bodies, rich in complex organic molecules such as amino acids, might have delivered the essential building blocks for life through their collisions with Earth. This theory aligns with the concept of panspermia, suggesting that life's ingredients could have originated from outer space. Research has demonstrated that conditions in space are capable of creating dipeptides, which are linked pairs of amino acids and crucial components for all living things. This discovery points to the possibility that early Earth was endowed with these organic compounds via comets or meteorites, thereby catalyzing the formation of proteins and other molecules necessary for life. A fascinating experiment that mimicked the conditions of space showed that when a mini-comet made of carbon dioxide, ammonia, and other chemicals was exposed to cosmic ray-like conditions, it resulted in the creation of these vital organic molecules. Further supporting this idea, recent evidence suggests that comets may have not only delivered organic materials, but also contributed significantly to Earth's water supply. The period known as the Late Heavy Bombardment, when Earth experienced numerous impacts from comets and asteroids, could have been a crucial phase in delivering both water and life's building blocks to our planet. The Stardust mission, part of NASA's Discovery program, marked a significant milestone in space exploration as the first American mission dedicated solely to studying a comet, and the second robotic mission designed to return extraterrestrial material from beyond lunar orbit back to Earth. Launched on February 7, 1999, Stardust's primary objective was to collect samples from the coma of Comet Wild 2, along with interstellar particles, and return them to Earth for analysis. The spacecraft, weighing 560 pounds, utilized a unique substance called aerogel to capture comet and dust particles without altering their shape or chemical composition. After an exploration that included a gravity assist maneuver around Earth and a flyby of asteroid 5535 Anne Frank, Stardust successfully encountered Comet Wild 2 on January 2, 2004. The mission returned over 10,000 particles larger than 1 micrometer from Wild 2, providing invaluable insights into the composition of comets and the early solar system. The sample return capsule safely landed in the Utah desert on January 15, 2006, concluding a monumental 2.9 billion-mile journey. Following its primary mission, Stardust embarked on an extended mission. Stardust Next, new exploration of Tempel 1, to revisit Comet Tempel 1, which had previously been explored by NASA's Deep Impact mission in 2005. On February 14, 2011, Stardust Next flew by Tempel 1, capturing detailed images of the comet's nucleus and the impact crater created by Deep Impact, marking the first time a comet had been visited twice by spacecraft. This flyby provided a unique opportunity to study changes on the comet's surface over time and contribute further to our understanding of cometary processes. The mission's success was underscored by its low cost and the significant scientific return, particularly the analysis of the returned samples, which revealed the presence of organic compounds and suggested that comets might have played a role in delivering materials crucial for the emergence of life on Earth. Stardust Next completed its mission with a final transmission on March 24, 2011, after depleting its fuel, bringing an end to a remarkable 12-year journey through the solar system. The story of Stardust is like a cosmic detective story. By chasing down comets and collecting their dust, Stardust has helped scientists learn more about the very stuff our solar system is made of. It's helped answer some big questions, like where the building blocks of life on Earth might have come from. Comets, it turns out, are not just simple balls of ice and rock. They're complex, intriguing worlds that carry secrets about the early solar system, and possibly about how life started here on Earth. Every piece of comet dust that Stardust brought back is like a clue in unraveling the mystery of our place in the universe. It shows us how exploring space and studying these ancient objects can help us understand more about our solar system's past and even our own origins. It's a reminder of how much is out there waiting to be discovered, and how missions like Stardust pave the way for future explorations, continuing to push the boundaries of what we know about the cosmos. NASA did something really cool with a mission called DART, which is a big deal for keeping our planet safe. Back in November 2021, they sent a spacecraft to see if they could bump an asteroid off course. This was important because if a big asteroid was heading our way, this could stop it from hitting Earth. They chose a pair of asteroids named Didymos and Dimorphos for the test, with Dimorphos being the one they wanted to hit. On September 26, 2022, DART smacked right into Dimorphos at a really fast speed. This wasn't just a random crash, it was a well-thought-out plan to check if we could make an asteroid move a bit off its path. They picked Didymos because it wasn't going to hit Earth, so it was safe to try this experiment there. By hitting Dimorphos, they hoped to change how it moves around Didymos a little, showing that we might be able to push away an asteroid that could be dangerous to us. The cool part is that the mission worked even better than everyone thought it would. The reason Dimorphos started moving differently wasn't just because of the crash. A lot of stuff got thrown off the asteroid when DART hit it, and this stuff flying away helped push the asteroid even more. This meant that the mission did a really good job at showing we can change an asteroid's path. Lots of people and places helped with the DART mission. NASA worked with SpaceX to launch it, and teams from all over the world, including universities and space agencies like the Italian Space Agency, pitched in. The Italian Space Agency even sent a small satellite called Lycia Cube to take pictures of the crash, which helped everyone see what happened. Also, two big telescopes in space, the James Webb Space Telescope and the Hubble Space Telescope, watched the crash together. This was the first time they both looked at the same thing in space at the same time, which gave scientists a ton of information about what asteroids are made of and how they behave when they get hit. In another exciting mission, NASA sent a spacecraft called OSIRIS-REx to grab rocks and dust from another asteroid called Bennu. This happened on September 24, 2023. It's a big deal because the stuff it brought back could tell us secrets about how the solar system started and maybe even how life began on Earth. After dropping off the rocks, the spacecraft got a new name, OSIRIS-APEX, and it's off to check out another asteroid called Apophis. A space-time capsule? The OSIRIS-REx mission marked a significant leap in our understanding of asteroids and their potential to reveal the early solar system's secrets. Launched on September 8, 2016, OSIRIS-REx embarked on a journey to Bennu, a near-Earth asteroid. This mission was about reaching Bennu and bringing a piece of it back to Earth. After years of preparation and travel, the spacecraft successfully collected samples from Bennu's surface on October 20, 2020. Bennu was chosen for this mission because it acts as a time capsule from the dawn of our solar system. Being a B-type asteroid, it's considered primitive and unchanged since its formation. This quality makes Bennu an ideal candidate for studying organic molecules and carbonaceous material, both of which are crucial for understanding the origins of life and water on Earth. The mission faced several challenges, from navigating Bennu's rocky surface to selecting the perfect site for sample collection. The Nightingale site was eventually chosen due to its young surface age and the likelihood of collecting pristine samples. This site, located in a northern crater, promised freshly exposed regolith, offering invaluable insight into Bennu's composition and history. The sample collection was a historic moment, marking the first time NASA collected material from an asteroid's surface.